We have one more homework after next week.
Well,
So this week and then
this week and next week.
Then Friday.
So we have the homework due this week,
Yeah.
I was confused.
I'm sorry.
which will be due Thursday of next week.
Well, it's due Thursday of next week?
Yes. Because we have a homework due this Thursday,
Right. Oh, well, yeah.
and we have, which therefore another one will open up on Friday,
Right.
which will be due next Thursday.
Yeah, some of the
But we will
homework.
not get another homework opening up on Friday because there's
But we will
nothing-
get the points.
Yes.
Okay.
Yes.
Ostensibly according to the syllabus, if you have done all of the other homeworks.
Yes,
Oh,
I
yeah.
will.
Yes, I've done all of them.
So
I mean,
yes,
if
there
you
are,
don't do the next two.
there are 16 points available for free simply for completing
Oh,
the 7 homeworks that were assigned.
okay.
Yes.
So
Which I
what
will
class
do.
are you taking? You're taking medical terminology.
Yep.
I forgot to look for that book. You gotta message me, girl.
I will.
Cause I forgot. It's in my nightstand at home. I kept all my books.
Okay.
Well, most of them.
Alright.
Yeah, this is how, so I had to copy and paste it to print it.
What?
Yeah, it wouldn't print from my printer like this.
What about like this?
It wouldn't print like that. I had to copy and paste.
Did not do that?
No, so I have it, so that,
Right.
I don't know what it's
Yeah. I did it simply.
I didn't either. I said, I'm gonna keep trying, keep trying, keep trying.
No. Yeah. I'll just have this case. Here you go, because you said you have problems with the printing. You should understand, I need it in my face on paper. I don't know what I'm gonna do in this digital world.
You don't know what?
I'm gonna do in this digital world, I like paper a lot, books and stuff.
I don't know
Damn
either.
trees.
We're gonna have to, maybe it'll read it to us, hopefully.
No, it probably will. Everything will be on audio. I like touching paper. At least today I brought money for snacks.
Today I bought snacks to bring money.
Either way works, right?
You're lucky you're not taking physiology next, girl.
I'm not ready. Although I talked to a friend of mine, she said human anatomy's easy. I'm like, okay. Okay. I know, right? She's like, all you have to do is memorize systems. I'm like, you're either really smart or
Oh, yeah, we do what?
memorize systems of like bodily function and stuff like that. But she's like, it's not hard.
Some of it's common sense, you know?
I could see that.
This one is not common sense, okay?
Psh.
Like medical terminology is common sense, like
Well,
you
yeah.
can match the words. When you get to reading that book, you're gonna be like, oh, this is, you're gonna have an A. I think I ended it with a B, like barely. I was close to an A, but.
Okay. It's like,
Cause the test was all like, if you remember those big words. I can't even think of how to even explain one of them, but.
yeah, because they like break it down. They break it down to how the word even came. And I'm like, I can kind of find my way around that. I think I can do it. I believe in me.
Good.
Somebody has to.
It will work, it's good, it's a really good class.
All right.
I mean, maybe, some of the teachers may be different than others, but it's a really, I took it online.
Okay.
Are you taking it online?
Yeah.
Yeah. I don't remember what her name was, maybe I'll look for my papers.
Yeah, it was a female.
Yeah.
Teachers it online. Man, I was looking over this chapter.
Is it hard?
What were your thoughts?
My thoughts were, good lord.
Good Lord, what?
Just, wow.
I feel like this class should have been taken straight out of biology,
That's true.
and then you would have remembered a lot of it, because a lot of stuff is
Oh,
still
yeah.
in and out.
I'll agree with you there.
So, yeah.
My test
right?
Yeah.
I took it, and the whole time thing didn't pop up, like how much time I had left.
Okay.
Turns out my computer froze. So I tried to save every question, but I couldn't. So I only got like 14 questions saved. And I had to refresh it. So at the last 20 minutes of the test, what happened was those 14 questions were saved, but I had to do everything else. So I basically guessed. Like,
How did you do?
I got a 77%.
Are you happy with the 77%?
I'm
guess?
excited with the 77%.
Mine almost died in the middle of me. I was like, I heard
So-
myself,
so
I
you're
was
saying
like,
you
why did I
took
charger?
2/3 of the test in 20 minutes.
Mm-hmm. Nope.
Wow. So that's some gut responses right there.
So you're remembering this stuff.
Yeah.
Yeah.
Okay. I did it, and then just like it freaked out on me. My computer freaked out.
Mm.
So, yeah.
And then you freaked out.
Yeah.
The next time, or I should say next time, because there won't be that much time to do it, but I should say, and I believe I may have said at the beginning of class, that if there is a computer glitch or something like that, just email me and let me know. Because what I could have done, if it wasn't at 11:59 p.m. on Sunday, was reset your test. So that's the nice thing about having online tests where it's all random, especially if I haven't opened it up so that everybody can look at what the answers are. Then if you have a problem or a computer glitch or something like that, what I can do is I can just delete your current trial, and so when you open it again, you'll have your time limit and everything is back. It's almost like getting a second chance to take the test, except that it's going to be a completely different test, because you will get a different random set of questions. And so I don't allow multiple attempts at the same test, but it does make it very easy for me if somebody has a computer glitch, if their computer crashes or something weird like that happens, then I can reset it, and then you have, and then with this understanding, if you emailed me Sunday morning and I didn't see it until Sunday afternoon, then I might give you till, say, the end of Monday to finish it without penalty. But yeah, if you're like taking it at 11:50 and you're running out of time, then I'm not going to notice until Monday morning, at which point I might still reset it and give you the day, but because I'm not here to punish you for computer problems. I'm here to
Punish us for other reason.
Sure. I'm here to teach and or evaluate how much you have learned about or how well you can apply your understanding of the topic, right? And the only way to really do that is with an exam. Outside of course, just asking you guys to write really large essays for me or something. So, which I'm sure you guys would love to do, right?
No.
Every test being an essay test.
I like more math.
My history essay is due on Sunday. I got it down to where like I know what I'm gonna talk about,
Okay.
but whenever I try to write it, I can't think of anything. Like I blank.
Really?
So yeah, so I'm literally like I just set
My
my
bit of
essay up and now I can't write it.
My bit of advice would be start writing anything,
Yeah.
even if it's just like what you had that day, like what's going on that day. Even if it's not topical at all, just start writing it, and then try and start shifting it to talking about how much you hate having to write this essay on the subject of such and such. And then you can transition that into writing about the actual topic of the essay, and then you just have to make sure you go up and delete the first few paragraphs that you don't want to accidentally turn in. But it's writer's block, and the easiest way to get past writer's block is just to write anything. And it doesn't matter if it's crap, you can go back and be like, this is all crap, and I need to edit this sentence, and this sentence is repeated, and it doesn't matter, you can edit that stuff out. It's so much easier to edit bad writing than it is to write good writing,
Yeah.
right? So just getting something on paper should get past the writer's block. Because once you start typing, your thoughts are going to flow, and it might start coming out. But yeah, jumping into the pool can sometimes be daunting.
Do you have like everything pre-written, like a setup? Like,
No.
oh, you should do that.
I just have what I think I'm gonna talk about and that's it. Other than that, like I can't comprehend anything.
Is there like an article about it?
No.
Well, you gotta be careful about that, because then you're risk plagiarizing the article.
But yeah, but if
Yeah.
you like write like your notes about the article, like questions you may have, you can turn that into something. Like if you have a piece of work that you read that pertains to the topic, you can kind of work with that.
On the subject of questions you may have, does anyone have any questions about the exam other than the harrowing story of finishing it in 20 minutes?
Wait, what?
Your harrowing story.
Your-
finishing
Oh.
it in 20
Your harrowing story of finishing the exam in 20
I thought you
minutes.
said the last exam, we're gonna have to finish it in 20 minutes, and that.
No, that was not what I was implying at all, no. On the subject of the last
So
exam,
now
it
that
will
you
be-
did it, you know.
Yeah. Now you have jinxed yourself. It will be in 2 weeks.
You've proven it's possible.
It will be over presumably 3 chapters, so the remaining 3 that we have on the syllabus. If there's time, we could move on and deal, I think there's one more chapter.
Chapter 18, yeah, I saw that.
But it is not a requirement per the syllabus, so we'll see how that works. Well, it just all depends on how we get through this. So yeah, it'll open 2 weeks from this previous Friday, right? So not this Friday, but next. And it'll be the last thing that you have to do. So it'll open on a Friday, just like all the others. It'll close on a Sunday night, just like all the others. The only difference is that there won't be a window for an oops, which so far, no one's really needed. So that shouldn't be a problem. Everybody's doing a pretty good job of making sure that they get the test done in the intended window. So when you're done with that test, you're done with the class. That's the way it works. No other problems. There will be one more homework, since that has been asked and answered a couple of times already. That will open up this Friday morning-ish. And it will be due before class on Thursday, so it'll be the last class that we have as well. There will not be another homework opening up that week because we don't have class the following week for you to turn it in, right? So the homework that opens up this Friday morning will be the last one that you will have to do. And presumably if you have taken or finished or even attempted all of the 7 previous homeworks, you will get credit for the 8th free homework assignment for free. That's the way that works. At least according to the syllabus, that's the way that works. I might decide to be nice. Maybe. There's really only a couple of you that would need me to be nice anyway, so.
You should.
You think so? All right, let's talk about chapter 15, shall we? Unless, I say we didn't really, does anyone have any questions? I did get an email from one student about some questions on the exam. One of which was correctly scored, the other one was ambiguous enough that I felt uncomfortable about it after further justification or further thought, so I gave credit for that one question to that student, and then went into the question pool and changed it. So, for future students will benefit from the lack of that particular degree of interpretation that I was uncomfortable with on that particular question. If you guys find any questions that are like that, I may go through and do similarly with you. I am especially concerned, given the fact that the way I had to import these questions, I'm especially concerned with questions that were like the question wasn't finished, like, what's this thing, or like the sentence obviously cuts off halfway through. The way I have to import the questions with commas, if I miss a comma somewhere, then whatever comes after that comma is going to get cut off, and I may not notice that it's gone. So if there was a question, there was like, I don't know how I was supposed to answer this, I just guessed D or something like that, like, then let me know about that, and I'll give you credit for it if you missed it.
Can you tell us which
And
one?
the pictures didn't even pop up either.
None of them?
No. So I had to right click.
And you
And then-
still?
Yeah, I had to right click and open it in a new window to look at the pictures.
Huh.
Yes.
No one else had problems with the pictures, right?
This is automatic gauge right here.
Okay. Just PTSD from
Just for that
chemistry
effort.
class?
My
Wow.
God, girl.
Wow.
What was that question for the curiosity? The one I missed?
No. No, I don't know, you'll have to go back and look. I'm concerned about questions like that. There was a question like that on the first exam. So it is where it, like, half the question wasn't there because I missed the comma when they imported it. And so because of the way it imports the questions, it assumes that like the thing is a comma separated file. So the question text is what's between 2 commas. Well, we use commas in common discussion and talk, right? So I have to manually go in and make sure that I remove all those commas, which is why you might notice in some of those questions that it flows a little bit like a run-on sentence. That's because I had to get rid of a comma in order to import that question. Well, if I missed one, then there might be a question that was impossible for you to correctly answer other than a guess, and if you guessed wrong, then I will go in and A, correct that question, B, give you full points for it, because it's not your fault that you missed it. As it so happens, the person who noticed those problems with the first test got them right, by sheer luck. So, but they noticed them and asked about them so I could go in and correct them, and didn't have to worry about correcting the grade. But if that is not your story, or if there is a problem, please let me know. I was also concerned about the images showing up. I'm glad that only one of you had that issue, and that everybody else it worked fine. It means that I'm importing everything right. I assume the images were clear enough that it was very obvious which chemical compounds you were looking at. Like there wasn't anything that was like totally. You always say no to everything. I should just change my question.
I got
so
two
that
little kids. No is my favorite.
I know how that works. I really do. No is my son's favorite word right now as well. He gets in trouble for that. We say too much, perhaps. All right, so if there's no questions about that, everybody's good. I'm fairly happy with it. I know it was a very conceptual test, but not everybody got an A, but our average was still in the high 70s, low 80s for a class. I'm okay with that. That's pretty good. As far as just kind of looking at how everybody is doing, I love to hand out A's, but I also like it to be just challenging enough that getting an A means you actually earned it. So there's the way that works. I don't like handing out F's, but I'm more than willing to do it if someone really, really wants one. So that's the way that works.
I just want an A would be lovely.
Yeah, there you go. All right, let's talk about lipids. You gonna work for me? You're not plugged in? I can actually have to use the keyboard today.
Oh yeah, wherever the dongle is, it's not plugged in.
I have to use the keyboard. Oh no! That's not working either. Really? Is that why it's not working? Was I on the wrong thing? I was on the wrong thing. Technology. I get along great. I swear I do. Really, seriously. Okay. Lipids. Biomolecules that contain fatty acids on a steroid nucleus. Soluble in organic solvents, but not in water. Tell me why not. Lipids are soluble in organic solvents, but not in water. Why not?
Not polar.
They're not polar, correct. Lipids have, or more to the point, lipids have a very long non-polar side chain, right? So it's the same idea, the same problem, I guess, that we had with our alcohols, our aldehydes, ketones, and carboxylic acids, right? That once you got a carbon chain that was past a certain number of carbons, the solubility in water started to drop precipitously. Too much non-polarness makes you not get along with water, because water doesn't know how to hold on to you, it doesn't know how to interact with you, and it makes you thermodynamically unstable. So, you get kicked out of the treehouse, which is how the whole hydrophobic, hydrophilic thing works. Comes from the Greek word lipos for fat, and it is an incredibly important biological molecule and macromolecule because it is featured in all of your cell membranes. We also have a lot of fat-soluble vitamins, steroid hormones. There's the thing about these guys, like dissolves like. So, do you think a steroid hormone, if I give you the up front, something that we haven't learned until later, but hopefully you have learned previously in many a class, your cell membranes are lipid bilayers, phospholipid bilayers, so they are small concentrations, isolated concentrations of lipids. So, since like dissolves like, for these hormones that we haven't talked about very much, what do you think is special about steroid hormones? Do you think they would be able to get through the cell membrane and enter the cell, given the fact that they are made out of lipids, and the cell membrane is made out of lipids, and if like dissolves like, then what could these hormones do?
Destroy cells.
No. Possibly, if that's what their physiological reaction is, but more specifically, steroid hormones can dissolve, if you will, into the membrane of a cell. A lot of the hormones that your body uses are charged hormones that are not that are water soluble. That's why they get along and float around in your bloodstream, which is predominantly water. But because of that, they cannot get into your cells. It's like having a mailman who leaves his mail in your post box, but if you can never leave your house, that message will never get to you. But steroid hormones, they can slip into and therefore right back out of the membrane. And if they happen to slip into and out of the inside of your membrane, then they can transmit chemical messages from somewhere in your body to somewhere else in your body, and they don't have to leave a message at the door. They can get through the membrane by themselves and actively trigger cellular responses. Whereas most of the other hormones have to stop and leave a message at the door. We're going to talk about how that signal transduction works sort of a little bit at the very end of this chapter, and we come back to that. All right, so different types of lipids. We have fatty acids, which are these guys here. These are a carboxylic acid functional group attached to a long hydrocarbon chain, a linear hydrocarbon chain. Take the word linear with a little bit of a grain of salt, because what do we know about double bonds and what effect they have on the straightness of carbon chains?
109 degrees.
It bends them, right? It turns it from 109 in a tetrahedron to 120 in a single plane, right? So it bends that bond. So we're going to call this a straight chain fatty acid. That does not imply that it is actually straight. It implies that it is not circular. It implies that it is not a steroid, which, as you can see, is still a lot of carbons, right? But it is a lot of cyclic carbons. A lot of carbons in a ring structure, a poly ring structure. So, the general structure, we have our steroids off by themselves as a special class of lipids. Our fatty acids can be broken down into multiple other groups in the ways in which we use them. We have waxes, which is a fatty acid combined with a long chain alcohol. Tell me, please, before we get to the slides that specifically describe it, what type of bond does that little dash right there represent? What type of bond is this? Yes, it is a single bond. But it is a single bond that is a specific type of bond. A specific type of bond that we would be able to name as a functional group. In other words, we could take that wax and we could perhaps give it a name based on that bond, in the same way that we give a carboxylic acid a name because of the shape of the bonds of oxygen that's there. So we have a long chain alcohol with a fatty acid. What's reacting together between that long chain alcohol and that fatty acid? I'll give you one other hint. It's very topical for the test that you just took and therefore likely flushed. Carboxylic acid on the fatty acid, right? Because when we look at this guy right here, what's going to react out of all of that? Have we had a lot of biochemistry so far where we have the carbons and long chain carbon chains reacting with anything, really? Okay.
Yeah.
Sorry. All right, just making sure it wasn't something I needed to respond to. So, if it's not going to be any of these carbons, it's going to be that carboxylic acid. So what's going to react with something from the alcohols? Long chain alcohol. The hydroxyl functional group of the alcohol, right? So what do you get when you combine a carboxylic acid and an alcohol? What type of bond is that? What type of molecule does it produce? And don't say wax. Somebody was going to go there. And the correct answer is ester bond. Is that what you were thinking? Okay, you read it.
I was scared.
Well, am I that scary?
A little bit.
Do I jump down your throat if you say something wrong? I'm like, no! Never talk again! I don't think I've done that so far. Yeah. So,
an ester bond. Long chain fatty acid with, or long chain alcohol reaction with a fatty acid. Now, here's a triglyceride. Here's your glycerol combined with 3 fatty acids. Anybody care to take a guess what type of bond it is that's linking that glycerol to those fatty acids?
Ester bond.
Once again, an ester bond, very good. Here we have a glycerophospholipids, we have some ester bonds here, combined with, instead of a 3rd fatty acid, we now have a phospho bond combined, a double, with that same double oxygen there, except this is not just an ester bond, we call it a phosphoester bond, because it's still that that double bond O, right? That delocalized double bonded oxygen right next to a single oxygen, so it's a phosphoester bond. And in this case it would be phosphodiester because we're linking it to both the glycerol and an amino alcohol. Because it is the alcohol group on the glycerol that is reacting with the fatty acids or the phosphates in order to form that ester or phosphoester bond. And then of course we have sphingolipids, which is a nifty little group that we're really not going to... Like sphingolipids is kind of a black box that we're just going to leave as mostly a black box, which is just another way to build a fatty acid, or a lipid I should say, except instead of using glycerol as the linker, you're using a sphingosine as the linker. So, let's talk about fatty acids. The metaphor that they're using here, which I actually like, is both in terms of metaphor and also in terms of chips. We have some chips here that are stacked up nice and neat. We have some chips here that are just kind of exhibited in a pile. These are more like Lay's or something like that, and these up here are Pringles. So, what's the difference? Pringles stack nice and neat in an orderly fashion, whereas the Lay's do not stack nice and neat because they have odd shapes and bumbles and ridges and weirdness to their shape, and so therefore they're just going to be trying to stack them all up, they're just going to fall into a pile. So what's the metaphor here? This is exhibiting the structural characteristics of a fatty acid that would be a solid at room temperature, because it is easy and nice and neat to stack. This is exhibiting the characteristics of a lipid or a fatty acid that would be a liquid at room temperature, because it is not nice and neat. It does not easily stack, and so therefore if you did try and organize them, they would just kind of fall all over themselves into something that would look a lot like a fluid, right? Instead of having a nice structure and organized state like something we might call a solid. Fatty acids, long, unbranched carbon chains. Why do we need that unbranched carbon chain right there? What other macromolecule have we discussed where branching is part of the systemic description of that macromolecule? Carbohydrates, starches, cellulose, long branching hydrocarbon chains, right? Those were cyclic hydrocarbon chains in the form of glucose. So here we have long unbranched carbon chains with a carboxylic acid group at the end, a functional carboxylic acid group at the end. Typically we're talking about anything 12 to 18 carbon atoms long. That would make it well within the boundaries, or I should say well beyond the boundaries of a carboxylic acid that would be soluble in water, right? Does anybody remember ballpark about where do you start running into problems with carboxylic acid? How long of a carbon chain can you get before you start running into solubility problems? 6 is where we get soluble, and 7 and 7 plus was partially insoluble to completely insoluble, right? So we're talking about anything beyond that is going to have some major problems. So 12 to 18 on average. Can we appreciate why even though there is a carboxylic acid group, these guys are insoluble in water? There's just way too many carbons here. There's way too many non-polar carbons. No dipoles there, no partial charges in order for water to hydrogen bond with it either way to allow it to maintain solubility. We call them saturated, a saturated fatty acid, when they do not contain carbon-carbon double bonds or carbon-carbon triple bonds. In other words, when we have saturated the possible locations for hydrogens. if all of the carbon-carbon bonds are single bonds, then there is no other place for hydrogen to go, and therefore it is saturated. We call it unsaturated when there is still places for hydrogen to go. In other words, when we have carbon-carbon double bonds, or theoretically, I guess, triple bonds, but mostly we're going to be talking about double bonds. And you can have more than one. In fact, when you've got 18 carbons, there's a lot of places for double bonds to go. But if we have one or more, we are considered an unsaturated fatty acid. If we have none, then we are saturated. If we're going to draw them, you get something like this. So we have that nice, relatively linear 109 bond angle here with our hydrogens pointing up the top on the top and pointing down the bottom on the bottom, with of course our CH3 group at the end with everything just kind of pointing out and away. So we have our carboxylic acid group at the end, we have a methyl group at the other end, and then we have a whole bunch of CH2 functional units in the middle, right? We could also draw this in the condensed format, the condensed structural format as that methyl group, the carboxylic acid group, and then CH2 to the 10th. So we have 10 CH2, or 8, or 12, or 18, or however many there happens to be, but in this particular molecule, that's the way it's drawn. Here's where I mentioned once before, you will sometimes see that carboxylic acid drawn as COOH. If I were to actually take the time to use that in some of your test problems, it would have made it a lot more easy for me, because some of the questions were annoying in having to use a three-dimensional drawing program just to get that double bonded oxygen hanging off the top. This could have made it easier for me to just draw it like this, but I wasn't certain that that would be recognized since I only really mentioned it once or twice. You could, of course, draw it out all the way like this with all those CH2s drawn out. Or we could draw it in the line. Why do we not have any hydrogens hanging off all of this? Because we were just assuming in that particular line model that anything that is not drawn, any bond that is not there, is a carbon-hydrogen bond, right? Which is why we have the double bonded oxygen and the OH there, but any of these other bonds are just hydrogen bonds. Up to and including the 3 hydrogens hanging off that guy in the end, because that's the way that works, right? Saturated when there are only single carbon-carbon bonds. So here we have lauric acid, comes from coconut, CH3, CH2, 10, COOH, drawn like this. Here we have myristic acid, 14, 0, so 14 carbons. You can get that from nutmegs. Here we have palmic acid from palm oil. Here we have stearic acid from animal fat, 18 carbon chain. Completely saturated. What do you notice about all of these? How many double bonds do you see between any 2 carbons? None. That is why they are called saturated acids. Now, unlike previously when we had these nifty little rules for how to name things, right, based on how many carbons were in a thing and what bonds there were that labeled them, you'll note that when we're dealing with these guys, because we could still do that, right? What would this be? What would the IUPAC name for this guy up on top be? Well, what's the first thing we would do if we were trying to name it? What's the functional group that's most important that we see there?
Carboxylic acid.
Carboxylic acid. So it's going to be a something or other acid, right? So how many carbons are there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. What's the name for something that has 12 carbons? I actually don't know. But there's a name for it, right? Just like butyr is butene for 4, pentene for 5, right?
Dodeca.
Dodeca. So this would be dodeca carboxylic acid, dodecaoic acid. If we really wanted to have something that what's that?
Have you heard the phantom tollbooth replace UD?
Dodecaoic acid. I don't know. I don't get the D&D reference there.
One of the character. Oh, you roll a D12. And
Dodecahedron. Sure.
Yeah. But in Phantom Tollbooth, he actually has to talk to dodecahedron when he gets to the bath. Yeah.
I see. All right. So, point is that when we're discussing these fatty acids, we're not going to be using their IUPAC name. We're going to be using their common name. which means that I'm either implying that you will need to simply memorize that this is the shape of lauric acid, or I'm implying that I will tell you how long a carbon chain in acid is when it comes to your questions, that you're not going to have to memorize other than just looking it up. I'm not going to expect you to memorize the names of 30 or 40 different fatty acids. That's not something that you will immediately need. But I am pointing out that there are ways to use isotopic nomenclature for naming these hydrocarbons. But because these things are so important for our diet, all of the ones that we're going to be talking about in this, as our discussion in this chapter, are going to come with common names. Lauric acid, myristic acid, palmitic acid, stearic acid. And so if you were asked to draw them, which you're obviously not going to be done, it's not going to happen on a test, I can't ask you to draw something. Here's some monounsaturated fatty acids. Palmitoleic acid or oleic acid, 16 or 18. What's the difference between oleic acid and stearic acid? Right. Oleic acid is an 18 carbon chain, but it has one double bond right there. Now, if we were to start throwing in other double bonds, would it be oleic acid? No, it would be acid. It'd be something other acid. Some other name, some other common name for that particular fatty acid. Where do we get oleic acid? Where do we find it? Olives, pecans, grape seeds. In other words, this is olive oil, a primary component of olive oil, oleic acid, and here we have stearic acid found in animal fats. Still the same number of carbons, but oleic acid has one double bond in it. It is not saturated, and its melting point is at 14 degrees C. The melting point for palmitoleic acid is at 0 degrees C. What's the melting point for all these other guys? These saturated fatty acids, 44 degrees C and up. So what would these guys be at room temperature? A nice balmy 27 degrees Celsius. They don't melt until we get above 44 or higher, then they're solids at room temperature. These guys melt at 0 and 14. So what state do you find them in at room temperature of 27 degrees Celsius? Liquid. Thus the oils that we described here. Fatty acids can come as polyunsaturated, which means they have at least 2, 3, 4, or more double bonds, polyunsaturated. Linoleic acid, 18 and 2. Linolenic acid is 18 and 3. Arachidonic acid, 20 and 4. And we have our abbreviated and line formats here. It gets a little hairy because you have to actually illustrate where the double bonds are. And so we have our CH3, CH2, 4, because we got 4 just regular carbon chains. Then we get into this double bond separated by a single CH2 before we can then have all of these CH2s at the end, CH2 7 once again. So I'm pointing that out so that you can understand what this means, why they have drawn it this way for you. Is this weird group here is where we get our double bonds from. That's why you get this thing down here. You have CH combined with CH, double bonded to CH here, repeated 4 times. That's just the double bond with the single carbon with a double bond, followed by single carbon, double bond, followed by single carbon, double bond, followed by single carbon, double bond. That's why they just have that group there, repeated 4 times. What are the melting temperatures of these guys? -5, -11, -50. So what would they be at room temperature? Liquids. Yeah. Arachidonic acid comes from meat, eggs, and fish. We don't have a lot of evaporation of oils out of fish at room temperatures. Haven't quite reached the boiling point, but we are well above the melting point, right? Alright, so here's that idea of cis versus trans. Unsaturated fatty acids, anytime you have a carbon chain where we have a double bond like that, you can have either cis or trans. The thing about these unsaturated fatty acids is that when you have a cis double bond, that nice, neat, linear molecule that we would otherwise draw, if we actually draw it with the appropriate bond angles, the fact that we have hydrogens on both sides, it means that that nice, neat line has now had a significant kink thrown into it. But if we have a trans fatty acid, that same bond angle is now leaving us with an otherwise still linear, in air quotes, structure, right? How well is this thing going to stack with other molecules just like it? Not so well. How well would this thing stack with other similar carbon chain fatty acids? Still pretty well. Almost all naturally occurring unsaturated fatty acids have one or more cis double bonds. Trans double bonds is an exceptionally rare thing to find in a naturally occurring fatty acid. So, there's this thing called essential fatty acids. We haven't talked about amino acids yet, but we're going to see this topic come up again as well. There are essential fatty acids. And what we mean by that is not the same thing as essential oils. It does not mean that they come in multiple fragrances to allow for your nasal pleasure. It means that you have to have them to survive, and you are incapable of making them, or at least incapable of making them to the levels that are required for your life. And so therefore, the only place you can get them is from the other things that you eat. They are essential parts of your diet because you can't make it yourself. We are incapable of synthesizing certain fatty acids that we need in order to survive effectively. We have evolved in an environment where we found those fatty acids in our diet, and therefore there was little to no selective pressure for us to develop the ability to make them ourselves. As they were present in our diet, we evolved mechanisms that require them. So if you do not eat enough of stuff that actually has them, your normal physiological function will be impaired. That's what the term essential means when we're talking about dietary fats or dietary amino acids. You can't make them. Alright, let's talk about some of the properties of these fatty acids, shall we? When we draw it like this, it's easy to see, but if you have long saturated fatty acid chains, you get a nice stackable orientation. You get strong dispersion forces between these long carbon chains, allowing them to associate with each other in a relatively easy and stable manner that does not involve or in any way require hydrogen bonding with each other. And so you get a nice organized stack, a nice organized structure. We could almost call it a crystal structure, if you will. And that is why these guys tend to have relatively high melting points and therefore are usually solid at room temperature.
Crystallized in lattice.
Crystallized lattice? Yeah, you could think of it kind of like that, yeah. The important part is not so much the exact nature of their physical structure as much as the fact that they are a solid at room temperature. So, unsaturated fatty acids, on the other hand, because of that double bond, or one or more double bonds, it's throwing a nice kink into that chain. These guys do not stack neatly on top of each other. They instead fall and fold around each other, which is why at room temperature they tend to be liquids, because they do not form these neat organized units. You can force them into a solid state, but what would you have to do in order to have that happen? And I'm not talking about hydrogenation yet. I'm talking about simply making oleic acid into a solid. What would you have to do? Take your bottle of olive oil and do what with it? Put it in the freezer. Well, no, fridge would work, yeah. Nice 4 degrees C. That would work. So different oils can be made solids, but you have to drop below their melting temperature in order for that to happen. Get it cold enough that even though they don't like to stack up, they will find some form of lattice structure that will allow them to take the shape of a solid instead of a flowing and fluid liquid.
Is that why Olean makes things liquid?
I don't get that reference either. Olean?
It was an oil they started using to make potato chips, and it caused certain people, especially if you ate a ton of it, to just beeline to the restroom. And sometimes not even make it, because without it working.
A little bit of anal leakage.
That was the word I was avoiding, yes.
Is that, well, so there was a dietary supplement that you could take. I don't hear much about it nowadays, but it was something that you could take along with your diet, and it would help to decrease the amount of fat that you absorb.
That's one of the, yeah.
Yeah, right. So it worked by preventing fats from becoming emulsified in water, so therefore preventing you from absorbing them. But what that meant was that it kept a large amount of the oils that normally would have been absorbed by your body in your intestines. And your intestines don't know how to handle that very much. And so yes, it's like, just imagine drinking a bottle of olive oil and what that might do to the, let's say, flow rate of your digestive tract. And that's sort of what it was like having that, or if you were taking that. It did decrease the amount of fat that you absorbed, but that didn't mean that it wasn't there, it just meant it didn't get absorbed, so it stayed in your intestine until you expelled it, one way or another, willingly or otherwise.
Oh, Lester, and Wikipedia calls it anal leakage, so I guess it's valid.
Yeah, there we go. That's actually part of the warning, was when you first started using it, there was literally, the packaging label was, may cause anal leakage, and they suggested that you wear dark colored pants.
Kind of reminds me of the HCG craze. Let's inject ourselves with HCG.
Oh, human growth hormone? HGC?
Also during the late 90s.
No, the pregnancy hormone.
Oh.
What?
Yeah. No, that one I'm not.
In the late 90s, they would sell this fiber that would absorb fat.
Okay.
Of course, but fiber likes to, especially when it's got fat in it. So people would have to have surgery to remove these impacted fiber.
Lovely.
Yeah.
Some fat balls that were clogging their intestines.
Fiber molecule.
Yeah, fiber fat balls, yeah.
People do a lot of weird stuff with that though, weight loss.
Right, well, weight loss supplements, it's the whole idea of like, I'm going to fundamentally change my life by taking a pill and doing absolutely nothing else to change my life. It's understandable that, especially in American culture, because we, like, chemically assisted living, like that's a thing, right? Like, oh, isn't there a drug to fix that? I have this problem. If I take this pill, it goes away.
Well, and the medical, I had a huge argument with my cardiologist. He's throwing his degrees and his honors out at me. He wants me to take, what is it, when you have high cholesterol? Basically, it cures your high cholesterol without you having to change your diet.
Right.
And I'm like, I'm not comfortable with that. So, a year later, I brought him a cholesterol test and said, the hell with your degrees.
Well, by changing your diet?
Yes.
Right, well see, here's the thing about American culture though. Most people don't want to have to go through a significant life change when they can just take a pill.
Look up the HCG thing. I mean, it's still a huge thing, and you can now get it. It used to be hard to get. You had to import from another country.
Okay.
And like when I worked at the hospital, nurses were shooting each other up with this stuff like crazy. Because it's literally, you put it in a needle, like you're injecting, you've got diabetes and you're injecting
Insulin.
Insulin.
So you're injecting HCG.
Yeah, it's just HCG because, think about what that does for a woman. Typically when you're
Right,
pregnant,
during
you
that
lose
first
weight.
period of, lose a little weight,
Because
your
of the-
skin gets so much healthier,
Yep.
and
your hair grows.
shiny, and
But, who wants to throw up? That's what it makes you do. And then it makes your body think it's pregnant so that it
right. It mimics
gets rid of the extra.
So for guys, this could be really traumatic.
Next time you're in a health food store, you'll find it, it's
The
still in there.
HGC drops,
HCG,
or HCG.
yeah, that's the hormone when you're pregnant, that's what they test you for, it has to double like every day. That means that your pregnancy's healthy.
You're never in this class shooting.
No, it was crazy watching nurses go around and going, yeah, this is the best diet ever, and we imported it from India or something, and I'm like, oh my gosh.
I have a friend who also used something similar, somewhat by metaphor, used something similar for their
I
diet,
like to live in that.
and it was just called breastfeeding.
So when
So,
we judge dairy cattle, you need to see a minimum of 5 ribs. Otherwise, she wasn't putting enough into her milk.
interesting.
Oh, yeah, that's true.
Yeah. Yeah, so this friend used breastfeeding as her weight loss methodology. So,
That's like using it for birth control.
yeah, sort of. Sort of.
And
Okay,
stupid
so-
mentality.
What's that?
Do you hear about the tapeworms?
Oh, yeah.
People are putting tapeworms into their body to lose weight.
This tactile generation.
Oh my goodness.
Well,
We're
it's
obsessed with being
perfectly, it's
thin.
100% natural.
That's
The funny thing is, you go to like other countries and they want you to have weight because that means you're healthy and to bear children. They don't want you like this big.
that's how it's.
Well, and that's the thing about tapeworms is yes, they will absorb a lot of the food, but they're still inputting it into biomass, and so it keeps you somewhat thin, but then you also have to periodically flush the tapeworms by killing them and then eliminating them.
And they take all your B12.
Right, yeah. And you're spreading them around constantly in your fecal matter because of all the eggs that they're making.
The best house episode ever was the girl who couldn't feel pain.
Oh, yeah, yeah.
And so he puts her on the table, pushes somebody outside of the OR, grabs a scalpel, and of course the surgeon that's about to operate panics. And he goes and he starts digging into her gut, and she screams and sits up. And he's like, nice try. And she lays back and watches as he perforates her intestine and pulls out 27 feet of tapeworm.
Yeah.
Oh, my God.
Yeah. I just seem to recall that. All right, let's talk about prostaglandins. So, prostaglandins.
I'm sorry, we go for tapeworms. Let's talk about length.
That's 2211.
Yeah, there we go. Prostaglandins are actually lipids. They're hormone-like substances that cells make. They come, or I should say, are a part of a group of eicosanoids. So we start with arachidonic acid, which is a polyunsaturated 20-carbon fatty acid. But then they differ by what we add to a 5-carbon ring that we get at the end of that. The primary function of prostaglandins within your body is by raising your blood pressure and causing contraction or relaxation of smooth muscles in the uterus. But they're also involved in inflammation. So here we have arachidonic acid right here with our four hydrocarbons that are double bond. We're going to form a link in that chain in order to create this ring structure at the end. So what we have when we're taking about analgesics for certain drugs, especially NSAIDs, non-steroidal anti-inflammatory drugs like aspirin, the way they work is by blocking the production of prostaglandins. So, chemicals that are produced by cells during injury that are there in order to cause or enhance, if you will, although I don't know if that's the right word that most people would think about when you're talking about it, but to enhance the sensation of pain, which brings us as a nice segue after the fact to the previous discussion of House, about how pain is not something that is naturally just occurring. It is a sense that your body has in the same way that you sense cold or sense sound or otherwise. So our ability to experience pain is because you have neurons that are throughout your body, and their sole job is to tell your brain that there is something wrong. These prostaglandins are chemicals that activate those specific type of neurons. They will tell your body that something is wrong via the pain response. And so non-steroidal anti-inflammatory drugs like aspirin, they block that prostaglandin synthesis. And so you have things that are causing pain or should be causing pain, but your cells are incapable of releasing the chemical molecule that lets your brain know that there is pain. So that is how they work to stop pain responses, is by preventing the synthesis of the chemicals that initiate that pain response in the first place. Of course, if the pain is bad enough that there are other chemical responses involved in the process, then they may not work terribly well. But if it's something relatively mild, then they can. Here's aspirin, here's ibuprofen, here's naproxen. Starting with ring structures that are highly modified with carboxylic acid groups and long branching chains. Naproxen, otherwise known as Aleve. Relafin, I've never heard of that one, Relafin. NSAIDs. Where have you heard of that term before? NSAIDs. When you're watching TV.
NSAIDs or NSAIDs?
NSAIDs. N-S-A-I-D.
Oh.
NSAIDs.
Just like incense.
Incense, yes, we burn it in our, we prefer patchouli or hemp, like now, maybe dragon's blood.
It's always no lovely Aleve commercials and everything else.
Right. There are NSAIDs cause or prevent the synthesis of prostaglandins, but there are also certain types of drugs that you should not take when you're on NSAID pain relievers. Drugs that are interacting with that prostaglandin pathway, and so you don't want to be taking something that you are literally preventing and or can be causing a reaction that is even worse because of interaction between those drugs, because of crossovers between those pathways.
Or you could have NSAIDs in the other medication and you're taking too much.
Right, and you don't want to risk having effectively an overdose of it.
Yeah. For your kidneys.
Yeah.
It's in your kidney failure.
For those of us with IgA nephropathy, little option for pain.
I've seen a lot of kids, they'll take things like aspirin or Tylenol or whatever to overdose. And they don't realize that's worse than taking some of a lot of other things. I mean, it'll just kill your kidneys.
Yes, well, if the whole point is to die.
Well, a lot of them do it for attention and think,
Right.
well, this is Tylenol, it's
Right,
just
yeah.
a medicine cabinet. It'll get me some attention but won't kill me
Right.
until they end up,
Yeah, I mean,
On dialysis
they'd probably be a
with
lot better if they just, went into the garage and got the gallon of antifreeze that their dad has, pop up the truck in the car and during the day, right? Instead. At least it'd be sweeter.
So my friend, he thought that, I don't know if it was Advil or ibuprofen, but he thought each of the pills were like 10 milligrams each.
Oh, geez.
And it said take 100 milligrams, so he took like 10 pills. So he had to go to the hospital. Yeah.
So you're saying your friend is bad at reading and math?
Yes. And he went to the hospital he had to get his stomach pumped or something like that.
Yeah, you don't want to take over 1,000 milligrams at a time.
Yeah. Can lead to damage to your liver and kidneys because of the way in which that chemical is detoxified and removed from your body.
You also don't want to take it every day. I know a lot of people will be like, oh, 2 Aleve every day. It can lead to stomach cancer and all this other kind of stuff. Because it's just a buildup in your system.
That's why you buy the buffer.
Yeah.
All right. So we already have a link between fatty acids and hormones because that's effectively, if not literally, what prostaglandin is. It is a chemical based off of a fatty acid that your body uses as a chemical messenger. So let's move on, because we're going to come back to that when we start talking about other fatty acids or other lipids that are also hormones. But let's continue on discussion of fatty acids with respect to health in terms of omega-3 or omega-6. You guys have heard of these, I'm sure, right? You eat a lot of fish because they're high in omega-3 fatty acids, and that's good for you for some reason, right? So, you ever wondered what an omega-3 fatty acid was? Well, now you will know. No, I just know that somebody told me they're good for me, so I just eat fish.
When I take this pill.
So they're from fish oils.
There you go. So, the omega part of that is based on where you find the last double bond in that chain. So an omega-6 fatty acid, normally remember when we start numbering things, we number them based on the thing that makes it what it is, right? And so a fatty acid is numbered, or I should say, where would you find the number 1 carbon, the primary carbon in a fatty acid? You'd find it right over here as the carbon that's attached to the oxygen, the double bonded oxygen in the hydroxyl group, right? The carbon that's part of the carboxylic acid group. So when we talk about omega fatty acids, that means that we are literally counting in the opposite direction. We start at the end, the omega. We start at the methyl end of that fatty acid and start counting from there. And so an omega-6 fatty acid is a unsaturated fatty acid where the first double bond that we find is at the 6th carbon. So what does that imply an omega-3 fatty acid is? Right, it's at the 3rd carbon from the end, instead of the 6th carbon from the end.
So if we can't make all the things
Arachidonic acid.
where do vegetarians get it?
You can get it from more than just fish, but fish are a good source. So you can get essential oils from multiple sources in your diet, you just have to get it from somewhere. So fish are not the only things, they haven't cornered the market on
You
the
even said meat
omega-3s.
earlier.
Yeah.
So.
Well, stearic acid comes from meat, and arachidonic acid here comes from fish oils. Other sources. Vegetables contain omega-6 acids. So the first double bond is at the 6th carbon, counting from the methyl end. Fish are high in omega-3, especially cold water fish. So the first double bond starts at the 3rd carbon, counting from the methyl end. Linoleic acid. I'm not even going to, okay, I will try that. Eicosapentaenoic acid. Eicosapentaenoic acid. There we go. Docosahexaenoic acid. Woo.
I should give you props because that was me.
Thanks. I was going to say, I'm not going to try it, and then I knew I was right about to say it. I was like, nah, actually, I am going to try it. All of these are omega-3s, though, because that last, or I shouldn't say the last. You could call it the last, I suppose. But the first double bond counting from the methyl end occurs at the 3rd carbon. So 1, 2, 3, that's where our double bond is. Now these guys happen to have different lengths. They have different number of double bonds, but all of them are omega-3s because the first double bond we find counting from the methyl end is at the 3rd carbon. So they're all omega-3s. Even though they have different numbers of carbons, they have different numbers of double bonds. But by definition, an omega-6 or an omega-3 fatty acid is going to be an unsaturated fatty acid, right? Because the whole point of the omega numbering nomenclature is because that tells you that there is a double bond in there somewhere, right? Probably more than one, but at least one. So what does this have to do with health? Cholesterol plaques that form in your blood vessels that cause your blood vessel or your blood pressure to spike. If you have high omega-3 fatty acids in your diet, then there is a link to lower tendency of blood platelets to stick together. You lower the tendency of platelets to form plaque, and you lower the tendency of the atherosclerosis to form in the first place, therefore reducing the tendency of heart disease. One of the most dangerous forms of disease is, in fact, I believe, still, the #1 killer of men, and recently I think also became the #1 killer of women. Not atherosclerosis specifically, but heart disease in general. The silent killer, because frequently we don't have much of a clue that it's coming until it's here.
Thanks to the US government.
I'm sure there are a lot of things that we could blame.
Thank you.
But, yes, if you were to look at general health of a lot of other cultures in a lot of other countries, that is not always the case. But yeah, here in America, we are #1 for heart disease.
Yeah, and the weird thing is African American women, they're the highest on that for some reason.
Well, you can find that with sickle cell. Good done.
Yeah, but that isn't going to affect women more than men. So,
Oh, I see what you're saying. If the government thing, I mean, we're still seeing what, these ratios of fat to meat on like hamburger.
Oh, you mean
chubs
like
and stuff.
FDA and the food pyramid and the suggested diet stuff?
No, I mean, the 1970s flawed studies into cholesterol and such that did not differentiate between HDL and LDL.
Right,
And so they just say cut it all out.
right.
And they also say cut out all saturated fat, which is where your flavor and your satisfaction comes from. It's also where all your water soluble vitamins actually get absorbed and transported.
Right.
And so people were eating more, it's not satisfying. Boy, buy the fatty hamburger and just eat less.
Yeah.
Enjoy it.
Yeah. All right, so that's the link of omega-3 or just omega fatty acids. That's what they mean. So now, when you hear about omega-3, omega-6, you have a better idea of exactly what it is that you're buying. May not be any really that much better informed about why, but at least now you know what you're buying. So let's talk about waxes and triglycerols. Natural waxes, we find them all over the place in nature, plants especially. The first thing that you probably think about when you think of wax is beeswax, and that's neat, and I think of that quite frequently too because I love bees, I love honey, I love mead. But at the same time, when I'm thinking about waxes, the first place I think about is actually leaves.
So what?
Leaves.
Oh.
Because it was the waxy coating of leaves that allowed plants to invade further into land. It's the waxy coating of leaves that allowed us to get anything larger than mosses. Where do you find mosses? Damp, moist environments. Not on the south side of trees. There's nothing to do with side of trees. You find them in areas where we get lots of water because mosses will dry out very, very easily. They don't get big, their leaves don't get big, and they have to live in moist environments in order to survive. It was the waxy coating on those leaves that helped in the movement from these small bryophytes to our ferns, which actually allowed plants to invade further into land and conquer more of land, giving the animals that followed them a reason to invade land, to eat them. So the first place that I think of when I think of waxes is plant leaves. But that might have something to do with my evolutionary biology background. Maybe unbiased. I will admit though, beeswax is also awesome. You can find waxes on skin, waxes on fur, feathers for good waterproofing. Ducks that are constantly cleaning and preening their feathers, birds that are preening their feathers in order to apply a little bit of oil to their feathers so that they can stay nice and waterproof and lay on water on a sheet. Let's talk about waxes. What are they? They are a combination of a fatty acid and a long-chain alcohol via an ester bond. We're talking about, therefore, 14 to 30 carbons between the two, or actually each of them 14 to 30 carbons. That large amount of hydrophobic carbon side chains as a nice, I don't even want to call it thick, but just as a relatively uniform layer, helps prevent the loss of liquids or the penetration of liquids from outside of the plant. It helps prevent plants from desiccating. One of the significant differences between major groups of plants is what we call C3 versus C4 plants. And that doesn't mean that the C4 plants explode when provided with an electrical charge, as cool as that might be. But it does have something to do with the way they photosynthesize. And one of the primary significant differences, in an oversimplified manner, is to describe C3 plants as plants that breathe, and C4 plants as plants that hold their breath. So C4 plants are going to be things like grasses and cactuses. What would you describe as kind of a common denominator between the environments of grasses and cactuses? Areas where you would naturally find lots of grasses or lots of cactuses. Would you call them nice, mild, and humid? Arid. Would you call them perhaps hot and arid? Yes.
Which was which?
Hot. C4 plants are hot and arid. C4 plants know how to hold their breath. And so what they do is they photosynthesize during the day to capture all of that sunlight energy. But what does it take to actually make sugars? We need CO2 and water, right, to make sugars with all that energy. Well, that's fine and dandy. But the way you get CO2 as a plant is by breathing, by opening up the cells that have it so that they can absorb CO2 from the atmosphere. Well, if you are breathing in CO2, guess what you're also breathing out?
Oxygen.
Well, yes, oxygen and water. And so what cacti do, what grasses do, is they will absorb all that sunlight during the day, but they will wait to actually fix carbon and make sugars until the night. Because at nighttime in the desert, what happens?
Temperature plummets.
Temperature drops.
Whatever.
And so the risk of water loss because of that extreme heat also drops. And so at night, a plant can breathe without risking the loss of a large amount of water. This is one of the reasons why you don't find trees in the desert unless you can find a nice underground water source for them to survive on, because they don't hold their breath. No matter how hot the day is, they have their stromata, they have the openings, the way their leaves breathe, the mouths on the surface of all their leaves are open almost all the time. They breathe constantly, and therefore in the hot days of the Midwest and Southwest, they lose a lot of water. Were it not for that waxy coating, it wouldn't matter. I keep going to get a drink from this like it would make a difference. I'm gone for 20 minutes. Typical waxes, here's beeswax. For honeycomb, we have a 14 plus 1, 15 plus another one, 16, so 16 carbon acid, right? How do I know that this is the acid on the left? Because it has the carbon with the double bonded oxygen, right?
Were you saying 16?
14 right here,
Oh, okay, got it.
plus 1 is 16.
Thank you.
And then we combine that with a alcohol that has 29 here and another one for 30 right there. So a 16 acid and a 30 carbon alcohol, that's how we get honeycombs. Canuba wax from the Brazilian palm tree, even larger acid, but the same alcohol on the side. Then we have the thing that I've never heard of. What's a jojoba bush?
You heard of JoJo beans?
Jojo beans? No.
Yeah.
I don't know what that is. This is one of those, like, I might look it up when I get home. Like, read it before I was like, what is? I don't know
I
what that
can't really describe it.
Yeah, jojoba bush.
Oil.
Also known as the goat nut,
Am
deer
I
nut.
saying it wrong?
Yeah.
Is this the HJ and not
Yeah.
the JJ?
Yeah.
Jojoba?
Jojoba.
Also known as goat nut, deer nut, pig nut, wild hazel, quinine nut, coffee berry, and green box bush. Southwest North America.
Different people.
Colorado, Baja.
Interesting.
I didn't know it was a wax. I thought it was
Alright, so that's waxes. What about triglycerides? Waxes are a combination of a fatty acid and an alcohol. A triglycerol is a combination of one or more fatty acids, or in the case of triglycerols, it's 3 fatty acids and a glycerol molecule. In all of these cases, we have esters that combine the fatty acids with the trihydroxy alcohol, so it's still just a fatty acid and an alcohol, right? Which is what a wax was. Fatty acid and an alcohol. Except this is a fatty acid combined with something that has 3 hydroxyl units. And so we're getting a triglycerol, a triacyl glycerol. This is what that looks like. Here's our glycerol molecule with our 3 hydroxyls hanging off the sides. Here are all of our fatty acid chains with the hydroxyl functional units of the carboxylic acid group hanging off the side as well. What does this look like to you? We create this triglyceride with 3 waters, and so this makes it a condensation reaction, right?
So, what's the last one? glycerol and this one's glycerol.
Okay, so we have the glycerol versus glycerol. So we have glycerol as a triglycerol here. And glycerol is the molecule that we're going to use to combine.
Okay.
So that is glycerol right there. What's that?
The last one didn't have the glycerol, right?
The last one here?
Last,
Yeah, but that's because these weren't glycerols. Then we weren't combining them with glycerol. We were combining them with a single alcohol. The point is, okay, perhaps I see where your confusion is coming from. Our waxes are combinations of fatty acids and single alcohols. So we're combining them with carbon chains that have a single hydroxyl group as a functional group. When we talk about our triglycerols, we're still combining fatty acids with an alcohol-ish functional group. It's still an OH right here that we're reacting to form that ester bond. But now instead of combining to an alcohol that has one functional alcohol group, one functional hydroxyl, glycerol is a 3-carbon chain that has 3 hydroxyls. So it's the same type of bond that we had in a wax. We're just repeating it with 3 different fatty acids. So we're still forming that ester bond that we had in the wax, except now instead of having a single chain alcohol, we have a 3-carbon alcohol with 3 hydroxyls. Thus the ability to combine 3 fatty acids into a triglycerol. Triacylglycerol. Or a triglyceride in terms of what we call them dietarily. So we can name these things. Glycerol tristearate. So we have the glycerol because it's been combined with 3 things. And then in this case it's been combined with 3 stearate fatty acids. And then we have the nice common name right there. So anything that we're talking about when we have something as part of the name as glycerol is going to tell you that it is a triglyceride of some sort that involved the glycerol as the bonding agent. You can get mixed triglycerides. So a triglyceride or triacylglyceride does not have to have the exact same fatty acid as all of its components. We can get different fatty acids as its component, like this one here. We have stearic acid and an oleic acid and a palmitic acid, which makes this just a mixed triacylglycerol. Is this going to be soluble in water? No, because we got a whole crap load of not very polar things right here, right? So no, this is not going to be soluble in water. What do we use triacylglycerols for? We use them primarily for energy storage. Animal fat is stored in the form of triacylglycerols. Animals that hibernate will store a huge amount of this as part of their fat for stores for the winter. As the temperature drops, they'll go into hibernation and their body temperature can drop nearly to freezing. Their respiration will drop to exceptionally slow. Their heart might beat just a few times a minute. They might breathe even less than that. There's hibernation, and then there's also false hibernation, where they don't quite go quite so deep, so they can still recover quickly. It takes a while to go into complete hibernation. It takes a while to wake up from complete hibernation. People that study bears that hibernate during the deep winter can walk into that, crawl into the bear den with little to no risk at all that they're going to have any trouble messing around with the bear, measuring it, picking up the claws, doing all sorts of interesting things, taking a blood sample, perhaps injecting some antibiotics or otherwise, because that bear is out. Estivation instead of hibernation, though, those guys, that's not quite so much the case. They're just kind of in a really deep sleep. Hibernation allows them to save a lot of money, if you will, on food costs for a period of the year, when there's otherwise not a lot of food around, when it's otherwise very expensive to be a warm-blooded or endothermic animal that's going to be burning a lot of energy just to stay warm in a really cold environment. Allow your body temperature to drop, like a lizard does, and it's not nearly as expensive. So you get the benefit of both worlds. You get to be a warm-blooded animal when you're up, awake, and moving around, and you get to mimic being a cold-blooded animal when it's really cold, and you probably wouldn't be able to find enough food to survive anyway. The ability of bears to hibernate, of groundhogs to hibernate, it's something that is being studied by science, by scientists. It's especially important if we're going to start talking about surviving extreme environments, if we're going to start talking about surviving, say, trips to Mars, or something even beyond that. Because it'd be a heck of a lot cheaper to just fatten somebody up and then shove them into hibernation for a 32-year trip where they age as if they had only gotten older by a couple of years, and they sleep the entire way.
Where do you know?
Yeah, exactly.
Wait, you could do that? Or can you
In
do that?
theory, if you could...
Tried it.
No,
You're working on it?
because human beings have not evolved a mechanism that allows us to hibernate. But bears can do it. They're a mammal. So, how do they do it? What physiological changes allow them to enter that hibernate? Like the bear's heart rate drops down, their breathing drops down to where their heart rate beats just a few times a minute. They're breathing once every few minutes.
But do they still age? Well,
Their metabolism slows down considerably, and yeah, they do age, but not at the same rate. There is a link between the rate of metabolism and aging. It's not a linear association.
Well, most aging is the destruction of the telomeres on our cells.
Aging is a lot more complex than that, but yes, that is one mechanism of it, yes. And
So-
obviously, if your metabolism slows down to a crawl, then the rate of cellular reproduction will also slow down to a crawl, yes. So aging would slow considerably. Fat stored in the form of triacylglycerols is the only source of energy for these guys that are hibernating. So they have to eat a lot of very high calorie food in order to get ready for the dead of winter. Otherwise they will starve in the cave. If you see a polar bear walking around in the deep of winter, do not get in its way.
it will eat
Because,
you.
yeah, because that is a bear that is close to starvation. That is a bear that is so close to starvation that its own mechanisms for hibernation brought it out, because otherwise it was going to die in the cave. So it is out looking for food in a period of the year when there is not a lot of readily accessible food. And guess what? You are food!
Yeah, but you're food year round. They're ridiculously aggressive.
That is also true, yes. Even if it's dead of summer, they still might eat you. But I'm just saying, the likelihood of that occurring is going to be even worse if they're exceptionally hungry. Don't go trying to hand feed polar bears any blueberries. I'm just saying.
So is this the same for beavers?
What's that?
Is it beavers don't hibernate, but their
That's
fat
right.
has like 14,000 calories per ounce. Iditarod racers eat it just to keep from dying.
I don't know if beaver fat is that much more calorically dense as much as perhaps just a good source of thick, because I mean if you're talking about people that were in that area, right, they can't just order it from Mexico or something. Like they can't order a nice good chunk of blubber off the whalers from Japan. Like I don't know if there's really that much of a difference other than just here's a big chunk of fat that's easy to store and therefore high in calories. Yes, fat is really high in calories. The problem is that we're really bad at using it. There is a bird, I may have mentioned this already, there is a bird, size of a sparrow, it flies from Maine to Brazil over the Atlantic Ocean twice a year. And it does so on the number of grams of fat that you find in a king-size Snicker bar. It's amazing. The problem is we can't actually burn fat. Most mammals, I don't know about bears, most mammals can't actually burn fat. What we have to do is take the fat, spend energy to convert it back into pseudo-sugar that we can then dump into the Krebs cycle to burn. Birds, on the other hand, they can just burn fat directly. They have a metabolism that allows them to skip all of that synthesis and conversion steps and just go straight into burning the fat, which means they actually get the full caloric value out of it. We lose a lot of that potential energy as we're converting it back and forth into something we can actually use. Alright, so draw the structure of a triacylglycerol. This is not so much something you're going to have to worry about doing on the test, because once again, I'm not going to ask you to draw something because that would require me to manually grade it. But still, let's do this for a moment. Let's talk about what we'd actually need. Glycerol tripalmityl oil is a triacylglycerol that has ester bonds between glycerol and the 3 fatty acids. So, we're given the name, we need the condensed structural formula with the ester bonds of how that works. So where would we find palmityl oil? Well, I looked into this earlier, and what you'd have to do is go back 5 to 10 slides and find the slide that actually drew this for us. It looks a lot like that. Where's the fatty acid? Here's our 3 ester bonds, right? Here's one of them, and the other 2 are immediately below it, right? So where's the fatty acid? On the left or on the right? Where's the carbon that's involved in the double bond? Right there. Which side of that single oxygen is it on? It's on the right, so our fatty acids are over here, and our glycerol is over here. Remember, it's the carbon that's involved in the ester, the carbon that's bound to that double bonded oxygen. That's the side that has the fatty acid. That's the side that was the fatty acid. And that is true both for fatty acid and triacylglycerol synthesis, as well as amide synthesis and ester synthesis. The carbon that's stuck, that really does not want to come off, does it? The carbon that's stuck to that double bonded oxygen, that's the one that belongs to the carboxylic acid, in this case the fatty acid. Alright, we are just about to 7, and I need to refill my water, so let's take a 10-minute break. Pick it up from here. We're at 32 of 83. We might be straying to some off-topic discussions a bit more than we should, but we also have a little bit of room in these last 4 lectures, so I'm not that worried about it. It is.
Yeah. It's not my place, but it's not help with me. But I'm confused about this one, because I'm trying to figure out if the pyrophone is this, or is it all of these. I mean, on this one, it's not gonna tell you which one got wrong.
Carbon. Did you look?
I'm
in
gonna
the
look.
book? You looked in a book for carbon?
I'm gonna go in and look and see what is that. Because I found one that just counts the, the slides over, and my phone
I
didn't
think
come up.
carbon needs to be in a separate. It was weird because I read somewhere like in the book that it wasn't. It was like something weird. But then, and that's why I got that question wrong, and I was just like, and then it later said it wasn't something. I think page 400. It was tricky. It was. So
You were paying attention.
I was reading that thing several times. It pissed me off. No, not that. No, that's a but
I haven't read your message yet.
whatever. Text me.
Yeah, I'll let you know.
Okay.
Because I'll probably take it tomorrow.
Appreciate it.
Right. In the morning, I have this time.
And see, I don't have this time anyway.
No,
Mine's at like 1 to 3.
I have to be up at 6, so.
I do too.
I do not have free time. I do it before all my daycare kids get there and all my kids get there. I feel like that's it. Crazy.
Today? Probably not.
I didn't think so.
The thing is, like, once again, like I just made the lectures, the next one, the next chapter is only like 63, it's a little bit shorter. And I don't know about 17 or even maybe, I haven't made that
17 seems short.
So, like, let's just put it this way, I do not feel any pressure to rush through the material,
Gotcha.
because we only need to finish 3 more chapters to get to the end of the course.
Yeah.
And so if the last day of class is not a lot of lecturing and has some room for questions or clarifications or something like that, then I'm fine with that. I could try and rush through just to make sure that we could shove in an extra chapter just for funsies.
I'm good. I'm really good.
Yeah, you're okay with that? You don't want to
I'll
just
go with this.
maximize your learning potential?
This looks like a lot of, like in chapter 17,
Yeah?
looks like a lot of DNA stuff, genetic code, viruses,
Yeah.
mutations.
My
So,
mom does.
It doesn't go too terribly deep.
no, I mean, I wouldn't know how deep this rabbit hole goes, because this is not my profession.
I ran a molecular genetics lab for 10 years, so.
Science for criminal justice.
Yeah, DNA fingerprinting, that was all.
I don't see what 18 is even about. Metabolism, digestion of foods, and metabolic pathways, passing, oxidation,
It's literally the last thing in the book, so. Glycolysis, Krebs cycle, urea cycle. So it would allow me to actually go into a slightly deeper understanding of the Krebs cycle for you guys, sort of.
We don't need to do that. We don't, at all.
I feel your wish to avoid it, but forgive me if I do not particularly share it.
Did I do something in Pandora's box?
No,
Maybe.
I'm not going to change the way we move through just because of that. It's just.
I mean, you could change it for the next class, just
Yeah,
not
there we go.
this.
There we go. Yeah.
Yeah.
Just try push a little harder as I'm moving through, just to give me just that much more time.
Mm-hmm.
There
Are
we
you
go.
doing this like
Look at
summer
that.
too?
No, I am signed up for. I don't know if there is one in the late summer, or if there is, whoever was teaching before me, I guess has dibs.
Mm-hmm. So you're doing fall?
So I'm no.